In section 11.5, we learned about parametric equations of lines in 2 and 3 dimensions. In this section, 11.6, we're going to learn about planes in 3 dimensions. First, to begin, let's talk about the planes that are going to be parallel to the coordinate planes. These have very particular equations in that they only contain one of the 3 variables. So to start out, we have an equation of the form x equals a, where the variables y and z are missing. This means that this plane can be a point extruded in both the in both the y and the z axis. And so in other words, it's a plane through the point a0, 0 on the x-axis, and then extending in either direction in the y or z. As a result, it becomes a plane parallel to the yz plane. Similarly, we have the equation y equals b, which goes through the point 0, b, 0, and is parallel to the xz plane, and similar, of course, here for z equals c. Let's look at an example of sketching one of these planes parallel to the coordinate plane. We have the plane y equals 2. So we want to move out 1, 2 on the y-axis. I'm going to go ahead and just fill in that dot to indicate that this is a point on this plane. And then I'm going to draw my plane in the following way. I'm going to assume that that point lies on that plane. And then I'm going to bring out its edges here parallel to the x-axis. Maybe bring it out a little bit further. All right, and I'm just going to note here that this is an infinite plane. And what I mean by that is this plane extends infinitely in the x and z directions. So this actually continues, and this right here is a point on the plane. All right, what we would like to do is extend this idea to planes that might be skew or not parallel to the coordinate planes. But before we do that, we need to utilize what's called a normal. So a vector perpendicular to a plane is called a normal to the plane. We've seen this term used before, but we've been using normal as an adjective, right? 2 vectors are normal if they're perpendicular to each other, or 2 lines are normal if they're orthogonal. Now we're using this as a noun. A normal is a vector that is perpendicular to the plane. We're going to use this idea or this notion of a normal to define a plane in 3 space. So to get started, what we need is a point, which we'll just denote P naught with components x naught, y naught, z naught, and we also need a normal to the plane. Right now we're just calling it a vector, and it has components a, b, and c. Then what we want to do is we want to define 2 new vectors. We have r naught, first of all, which is just a vector from the origin to the point that we have. And so you'll see that drawn right here in the picture, where the origin is somewhere down below, and then we're going from the origin to our point P naught. And then R is just going to be any other vector from the origin to any generic point on the plane. So you'll see R right here. Now, if we're trying to define a plane that goes through the point P naught and is normal to the vector n, then what that means is we want every single vector on that plane to be perpendicular to that normal. How do we quickly check perpendicularity, right? We check perpendicularity by checking that v dot w equals 0. That implies that v is normal to w. So using that same idea, what we're going to do is we're going to take our normal vector n, and we're going to dot it with r minus r naught. That is representing a random vector in our plane. So we're going from our point P naught to any other point P, generalized, on our plane. And in order for that to be normal, we must have that this dot product equals 0. It may seem silly to say it out loud, but remember that this is an equation, and in particular, do not forget the equals 0 portion. A lot of times students will compute the dot product and dot r minus r naught, but they'll forget to equate it to 0. All right, we have several ways of expressing this equation. So just to remind you here, we had stated that n is the vector with components a, b, and c. R is the vector with components x, y, and z. And r naught is the vector with components x naught, y naught, z naught. And so what we can do is we can flesh this out and we can write it in component form. So in this first expression, we're just literally replacing n with a, b, c, r with x, y, z, and r naught with x naught, y naught, z naught. So this is the first way to express the equation of the plane in component form. You can also carry out the dot product, right? So take a times the first component in your second brackets, and that gives you your first term, plus the product of the second terms, plus the product of the third terms. So this is called the point normal form. The reason it's called the point normal form is that, especially if you're in the case of the second one, you can quickly pull off a point and a normal. The point is just going to be the x naught, y naught, z term pulled off. And of course, the normal is just the coefficients a, b, and c. So that's point normal form. We also have what's called the general form, which is given here in Theorem 1. It says if a, b, c, and d are constants and a, b, and c are not all 0, then the graph of the equation ax plus by plus c, z plus d is a plane that has a vector n equal to a, b, c as a normal. The above equation is the general form of the equation. So from the general form, you can quickly pull off the normal vector. However, the components for a given point are lost after that dot product has been distributed out. All of those constants for the point have been combined to a single constant d, so you can no longer identify a point quickly. So let's move into our first example here. Problem 3 from the text says, find an equation of the plane that passes through the point and has the vector n as its normal. So they're giving us the two pieces of information we need here directly in order to compute this equation. We want to use the fact that n dotted with r minus r naught equals 0. So plugging in what we know, we have n is 1, 4, 2. And then we want to dot it with, remember, r is a generic vector, so it's just x, y, z. And then in each component, we want to subtract off the components of the point. So x minus 2, y minus 6, z minus 1, and this equals 0. Now for full credit, I at least want you to demonstrate that you know how to take the dot product. So one more step for full credit. So if I compute the dot product, I get 1 times x minus 2 plus 4 times y minus 6 plus 2 times z minus 1, and this equals 0. I would give you full credit on a quiz or an exam at this point. However, I will note that the book will always write their answer in general form. So let's just go ahead and do one more step here to get it into general form. This is x plus 4y plus 2z, and then just collect all of the like terms. There's negative 2 minus 24 minus 2 is minus 28 equals 0, or typically the book moves the constant to the other side, so it'll write it as x plus 4y plus 2z equals 28. And this is how they would write their answer in the back of the book. So when you're given a point in a normal vector, you proceed just by using that n dot r minus r naught equals 0 formula, and it's pretty straightforward from there. However, there are many ways to ask to find a plane with given conditions, and one of those ways is to give 3 points. 2 points is enough to determine a line, but it's not enough to determine a plane, so we need a third point to determine a particular plane. So if we're given 3 points on a plane, how are we going to find the equation of the plane? So first thing is that we need to use those 3 points to find any 2 vectors in the plane. Now there are many ways to do this, so just pick two of those vectors. Doesn't matter which 2 you find. That's going to give us 2 vectors that are in the plane. To find a vector normal to the plane, we're going to use that really handy property of the cross product that says if you have vectors u and v, then the new vector u cross v is perpendicular to both u and v. So the cross product is always perpendicular to the 2 vectors that you started with. So then we're going to cross the 2 vectors that we found in the plane to find a normal to the plane. Then we can pull it all together, pick one of the points, and use the normal that you just found to find the equation of the plane. Note that it is unimportant which point you use. Once you've found the normal, any point will do. So let's go ahead and do one of these examples. Find an equation of the plane that passes through the given point. So we have P1, P2, P3. So our first challenge is to find any 2 vectors on this plane. So I'm going to start by finding vector P1, P2. So I'm going to take the components of P2 minus the components of P1. So I get 2 minus 3 is negative 1, 1 minus 2 is negative 1, and negative 1 minus 1 is negative 2. And then find any other vector that lies in this plane. I'm going to find vector P1, P3, but you could have just as well, for example, found P2, P3. So P1, P3 is negative 1 minus 3 for a negative 4. 3 minus 2 is 1. 2 minus 1 is 1. So we have these 2 vectors. We now want to find a vector normal to it by finding its cross product. So I'm going to find P1, P2 crossed with P1, P3. And so across the top is always I, J, K. And then I'm going to put P1, P2, and P1, P3. All right, go ahead and carry out this cross product. So if I strike through the I row and column, I get this lower right 2 by 2 matrix. So when I compute the determinant, I have negative 1 minus a negative 2. So negative 1 plus 2 is going to give me 1. So I have 1 in the I hat component. Similarly, if I strike through J, my determinant is going to be negative 1 minus a positive 8. So negative 1 minus 8 is negative 9. But remember, when we're doing the J hat component, we always negate it. So it's going to become positive 9. Keep in mind that alternating sign here. And then finally, let me erase that line. Let's also strike through the K hat row, column. And our determinant here is negative 1 minus a positive 4, which is going to give me a negative 5. So this vector is going to serve as our normal vector. And now we can pull it all together using the equation n dot r minus r naught equals 0. So I'm going to take my n. I'm going to dot it with r minus r naught. Remember, r is just some generic vector with the components x, y, z. And then for r naught, I'm going to use P1. And I'm just arbitrarily choosing that point. You could have just as well used it, P2 or P3. So that's going to be x minus 3, y minus 2, z minus 1. And don't forget to equate this to 0 to ensure that all vectors on the plane are perpendicular to the normal. So I'm going to go ahead and flush this out to get it to standard form. This is x minus 3 plus 9y minus 18 minus 5z plus 5 equals 0. And then moving all of the constants to the right-hand side, we get x plus 9y minus 5z equals, let's see, I have 21 minus 5 is going to give me 16. All right, and so that is how you're going to find an equation of a plane given 3 points on the plane. All right, a couple of notes here before we move forward. I mentioned this verbally, but this first note says that once you have chosen your normal, then the equation of the plane is independent of the choice of the point that you're going to use. So what's going to happen here is, in the previous example, had I used point P2 or P3, it might have looked different in the setup, but once I distributed and carried out the dot product and collected like terms, this constant term 16 over on the other side was going to be the same no matter what point I used. Now, what's important here is that you have already chosen the normal. So, for example, had I crossed P1, P3 with P1, P2, by switching the order of the cross product, that would have negated my normal. So I would have had -1, -9, +5. That might have made my equation look different with negatives, but it still would have been equivalent. Similarly, I might have found a different vector, for example, P2, P3, and my normal would have looked different. But once you've settled on a normal, your overall equation is going to be independent of the point that you're using. Our next note here is going to say how to determine whether two planes are parallel, perpendicular, or neither. So in order to do that, we want to identify the normal vectors from each plane, and then we're going to compare them. So if the normal vectors are scalar multiples of each other, in other words, that means that those two normals are parallel. Then if the normals of two planes are parallel, the planes themselves are also parallel. If the dot product of the normals is 0, then the normal vectors are perpendicular, and that means that the planes are also perpendicular. And then case 3 is just like, hey, look, if neither case 1 nor case 2 hold, then we just say that the planes are neither parallel nor perpendicular. So it's kind of ruling out the other two options. So let's look at some examples of determining whether planes are parallel, perpendicular, or neither. So the first thing we're going to do is we're going to pull the normal vectors off of each of these planes. So for the first one, I'll call it N1 is 3, -2, 1. Remember, those normals are just picking off the coefficients of x, y, and z. Similar for the second line, 6, -4, and 3. So first, just check at a glance whether these are scalar multiples of each other. At first, I was thinking they were going to be, because the x components are doubled, the y components are doubled, but we fail here in the third component. So I'm just going to make a note. There's no work to show. This is just by inspection. These are not scalar multiples. So I'm going to put an X next to this, and this is just indicating that we're failing the first condition, which means that the planes are not parallel. Next, let's check the dot product. So I want to dot N1 with N2. This is 18 plus 8 plus 3. I don't care what that is. All I care is that that's not equal to 0. So that means that these planes are not perpendicular. So now, just by process of elimination, I can conclude that the planes are neither parallel nor perpendicular. And so that's my conclusion here, neither parallel nor perpendicular. All right, we're going to do the same process here for B. You'll notice here that these are not written in standard form. So what we're going to have to do is move all of the x, y, z terms on one side for both equations. All right, so keeping that in mind, our n1 here is going to be a negative 4, a positive 1, and a positive 2. All right, and n2 is going to be 1, negative 1/4, and negative 1/2. All right, so first thing, by inspection, let's see if these two normals are scalar multiples. So I'm actually going to go in this direction. To get from 1 to negative 4, I would multiply by negative 4. So if I multiply negative 1/4 by 4, I get to 1, that's checking out. And negative 4 times a negative 1/2 would get me 2. So in this case, we have that n1 is 4 times n2. All right, so we're actually, and it was negative 4, right? So what this tells me is that these normal vectors are scalar multiples, which means the normals are parallel. And so finally, we conclude that the planes are parallel. All right, and so let's finish off problem 14 by looking at part C. We have our normal vector, n1 is 1, 4, 7. n2 is 5, negative 3, 1. These are definitely not scalar multiples. All right, no hope there. So let's check that dot product. So that's going to be 5 minus 12 plus 7 does come out to 0. So if the normal vectors are perpendicular, then the planes themselves are also perpendicular. So planes are perpendicular. All right, so that's how we're going to go through and check for parallel and perpendicular planes. We have a similar result, although it is distinctly different, for lines and planes. So when we think about lines and planes and how those equations are formed, recall from the previous section, 11.5, that when you have parametric equations of lines, the vector that you pull off lies along the line. Whereas when you have an equation of a plane, the vector that you pull off is perpendicular to the plane. So keep that in mind. So if you want to check for perpendicularity of a plane and a line, what you need is that the vector and the normal of the plane, so this is the vector of the line and the normal of the plane, are scalar multiples of each other. So remember, the vector of the line goes along the line, and the vector from the plane that we look at is normal to the plane. So if those two vectors are scalar multiples, it means those vectors are parallel, but the plane is perpendicular to the normal. So that means that the line will be perpendicular to the plane. This is distinctly different than what we talked about with two planes, right? So I'm going to highlight that up above. Up there, if the normals were scalar multiples, then those two planes were parallel. Down here, with a line and a plane, it's opposite. If the vector along the line and the normal perpendicular to the plane are scalar multiples, then that line and plane are perpendicular. Similarly, if we compute the dot product of the vector of the line and the normal of the plane, and we get that it's 0, that means that the line and the normal are perpendicular. But since the plane is perpendicular to the normal, that means that the plane and the line are parallel. And then case 3, if neither of the first two conditions hold, then the plane and the line are neither parallel nor perpendicular. So I didn't include any examples of this, but it's very similar to what we did in 14. And there are some homework problems that are going to cover checking how planes and lines are oriented in 3 space. All right, so moving along here, suppose that we have 2 planes with normals n1 and n2 and they intersect. So we have a nice figure here. Then the acute angle theta between the planes formed by n1 and n2. So you'll notice that angle right in here, that's the acute angle, not the obtuse angle, can be found using the following formula. So cosine of the acute angle theta is given by the absolute value of the dot product n1 and n2. Again, I just want to point out that this is an absolute value because this is not a scalar. The dot product outputs a vector. And then divided by the magnitude of n1 times the magnitude of n2, where on bottom there, those are magnitudes and not absolute values. So let's do an example of finding this acute angle of intersection. We are given 2 planes. We need to first pick off their normal vectors. So the normal of the first one is 1, 2, -2. The second normal is 6, -3, 2. And so we also need to find 3 different things. We need to find their dot product, first of all, n1 dot n2. And so that's going to be 6 minus 6 minus 4 for a total dot product of -4. We have n1, magnitude of n1, which is going to be the square root of 1 plus 4 plus 4, square root of 9, which is 3. And n2, its magnitude is the square root of 36 plus 9 plus 4, which is the square root of 49, or 7. So now we need only pull it all together using this equation up above, and let's find cosine of the vector. So cosine of the angle, that is. Cosine of theta is going to be the absolute value of -4 divided by 3 times 7. So we get 4/21. So finally, to find that acute angle, you would absolutely need to use a calculator in this case. So if I was having you do this on a quiz or an exam, I would ask for cosine of the angle, but we'll just find cosine inverse of 4/21 and just round this to the nearest degree. This comes out to about 79 degrees. All right. So we now know how to find equations of planes in space using a point and a normal, using 3 points. We also know how to find whether they're parallel, perpendicular, or neither. And we can find angles between 2 planes. So now what we'd like to do is practice finding equations of planes given various conditions. So let's take a look at 26. We want to find an equation for the plane that contains the line and is perpendicular to the given plane. All right, so we have several pieces of information here. So let's take a look here. Let's talk about some characteristics of our line. We can quickly pull off both a point and a vector along that line. So a point on that line is -2, 4, 3. And we also have the vector that is along that line, pulling off the coefficients of the t's in front of the parameter, is 3, 2, -1. All right, so when you talk about the plane that we're looking for, this point lies on the plane and the vector is along the plane. So these are both contained in the desired plane. All right, now we also have this other plane that our plane is perpendicular to. So the plane that's given, its normal, which I'm going to call N1 because it's not going to be the normal we're going to use, is 1, -2, 1. All right, and this normal is perpendicular, no. It's not perpendicular to our plane. We want our plane to be perpendicular to it. So our normal should be perpendicular to N1. All right, so how are we going to find a suitable normal vector? We already have a point on our plane, so we can use that point in our computation. But what we don't have is a normal to our plane. But we know that we want to be perpendicular to N1, and since V lies in our plane, we also want to be perpendicular to it. So our desired normal can be found by taking the cross product of those two vectors. Now, the order in which you take it is going to affect the sign of the vector, but either way, it'll be normal. So just pick whatever order you want to do. I'll do V cross N1. And let's calculate that cross product. All right, so we have 3, 2, -1, 1, -2, 1. And let's compute it out. So in the I component, I get 2 minus 2, which is 0. We always get negative for the j. So when I look at the j component, I have 3 minus a -1, which is 4. And then the k hat component, I have -6 minus 2 is -8. All right, the hard work is done here. Now I'm ready to pull it all together. I want to use my point, which I highlighted up above, and the normal, which I just found, to find my equation of my plane. So pulling it all together, I want n dotted with r minus r naught. So that becomes an x plus 2, y minus 4, z minus 3. And then remember, this has to equal 0 to ensure perpendicularity. And then go ahead and flush it out. The x terms are going to drop out due to that 0 in the normal. So I have -4y plus 16 minus 8z plus 24 equals 0. So if I keep these on the same side, that gives me 40 equals 4y plus 8z. The book typically reduces these, so if you just divide this whole equation through by 4, that'll give you y plus 2z equals 10. However, I don't require you to do any of this. As far as I'm concerned, at this line, I would give you full credit. The book is going to give you this answer for reference. All right, so that was a tricky one. You really have to make sure you understand where various vectors that are given to you are lying in relationship to the plane that you're trying to find. All right, this next problem, 28, find an equation for the plane through this given point that is perpendicular to this line. All right, so what we have is a point right away. And then we want to be perpendicular to this line. So in other words, the vector along this line can serve as our normal. So pulling off the coefficients in front of t, we have 1, 2, -1. And so we have all of the pieces that we need. We can pull it all together using n dot r minus r naught equals 0. And so we have 1, 2, -1 dotted with x plus 1, y minus 4, z plus 3 equals 0. So again, just at least carry out the dot product and you can stop anywhere past there. So this is x plus 1 plus 2y minus 8 minus z minus 3 equals 0, or x plus 2y minus z equals 10. All right, so you can see that there are many ways that the book can ask you to find an equation of a plane given various conditions. And that's why I always think traditionally that section 11.6 is more difficult than section 11.5. There are fewer ways to ask to find an equation of a line than there are to find an equation of a plane. All right, one more example. Find an equation for the plane through the points P1 and P2 that is perpendicular to this given plane. All right, so we have 2 points for sure, so we don't need to do any work finding a point. What we need to find is a vector normal to our desired plane. So if we take vector P1, P2, this is a vector that's going to lie in the plane. So 1 minus a negative 2 is 3, negative 1, and negative 1. All right. So we need our vector n to be perpendicular to this vector. All right, then we have this other plane, and I'm going to call its normal vector n1, and that normal is 4, negative 1, 3. Now we want our plane to be perpendicular to this plane, which means our normal needs to be perpendicular to this normal. So we need our vector n to be perpendicular to n1. So our usual trick, if we need to find a vector that's perpendicular to 2 other vectors, we need only cross them. So our n is going to be the vector P1, P2 crossed with n1. Fill in our matrix. 3, negative 1, negative 1, 4, negative 1, 3. All right, and in the I hat component, I have a negative 3 minus 1, gives me a negative 4. I'm going to put that negative sign for the j, just to remember that whatever sign I get, I negate it. So in the j, I have 9 minus a negative 4. So that is, what, 13? Negative 13. And in the k, I have negative 3 minus a negative 4, so that's a positive 1. So here's our normal vector, and then again, just using the n dot r minus r naught equals 0, we get the equation of the plane. So negative 4, negative 13, 1, dotted with x minus the point coordinate. I am going to use point 1, but again, you could have just as well used point 2. So that negative is going to turn into a plus 2. Then we have y minus 1 and z minus 4 equals 0. All right, and then go ahead and compute your dot product. Negative 4x minus 8 minus 13y plus 13 plus z minus 4 equals 0. And I'll go ahead and put it into general form. I'm going to actually move the x, y's, and z's over to the other side to make them positive. So 4x plus 13y minus z, and then leaving the constants on the side they're on, we have 13 minus 12, so that leaves us with 1. All right, to round out this section, we have one last theorem, and what it's going to do is it's going to give us the shortest distance from a point to a plane. And so you can actually add that little adjective in here. This is the shortest distance from a point in 3 space to a plane that's given by ax plus by plus cz plus d. And so how we're going to find that is on top, we're just evaluating that plane equation at the point that we care about, and then we're dividing by the magnitude of its normal. So just keep in mind here that the way the equation of the plane is set up is that the constant d is on the same side as the xyz term, as opposed to subtracting it over like we have been doing in a lot of our problems. All right, so let's practice using this equation. 44, find the distance from the point 0, 1, 5 to the given plane. So what I'm going to do is I'm going to just jump right in. I'm going to start by finding the normal vector from the plane, which is 3, 6, -2. And then I'm going to plug this all into the equation. So on top, I want to evaluate the plane at the point. So that's going to be 0 plus 6 minus 10 minus 5. And on bottom, I want to find the magnitude of that normal. So 9 plus 36 plus 4. That's the square root of 49, or 7. So on top, I have -9 over 49. Excuse me, not 49. Square root of 49, which is 7. And so my distance is 9/7 units. So that point is 9/7 units away from the given plane. All right, last example, we want to find the distance between these parallel planes. So the planes are given by x plus y plus z equals 1 and x plus y plus z equals -1. It is really tempting to say, oh, well, the left-hand sides are equal and the right-hand sides differ by 2, so they must be 2 units apart. That would be true if these planes were parallel to coordinate planes. However, these planes are tilted or skew, and so we cannot assume that that distance is 2. So if we want to utilize theorem 2, we need a point on one plane and then just use the other plane. So let's zero in on the first plane. Let's consider the plane x plus y plus z equals 1. Let's find a point on this plane. Certainly there are infinitely many points. If you wanted to work kind of hard, you could use, for example, the point 1/3, 1/3, 1/3. That satisfies this equation. But I don't want to work that hard because I don't like working with fractions. I like working with zeros. So let's just choose some of these coordinates to be 0. So if we let x and y be 0, then it forces z to equal 1. So what we just found is that the point 0, 0, 1 is a point on the plane x plus y plus z equals 1. I just arbitrarily chose to zero out x and y, but you could have zeroed out other coordinates as well. So now what we have is the point 0, 0, 1 and the other plane. So the distance from 0, 0, 1 to the plane x plus y plus z plus 1 equals 0. You'll notice that I moved that -1 over. That is given by d equals the absolute value of 0 plus 0 plus 1 plus 1 divided by the square root of 1 squared plus 1 squared plus 1 squared, right? That normal is 1, 1, 1. And so this comes out to 2 over the square root of 3. I am perfectly fine with you leaving your answer like that. Or if you wanted to rationalize the denominator, you could write this as 2 radical 3 over 3. All right, so this concludes our notes for section 11.6. Next up is going to be section 11.7, which is over quadric surfaces. We're going to get a lot of practice in graphing, so bring your art skills to the next video.